Good morning.
Morning.
Thank you all for being here today. My name is Allan Shtofenmakher. I am coming to you from MIT to present some results on a feasibility analysis of on-orbit debris detection using commercial star trackers. I'm planning to take about 12 minutes for my slides, so I'm hopeful that we'll have about 3 minutes for Q&A after all is said and done. With that said, this is a space traffic management conference, so it should be old news that the US Space Surveillance Network tracks over 23,000 resident space objects in low Earth orbit. And most of the objects in the catalog are larger than 10 centimeters in characteristic length. But NASA estimates that millions of RSOs are smaller than that in LEO. And a question that I get pretty often from people who maybe aren't as into STM or SSA is, why do we care about objects that are that small? But about 2.5 months ago, the ISS gave us a very good reason to care about objects that are that small. When something hit the Soyuz MS-22 spacecraft and coolant started leaking everywhere, rendering the spacecraft unsafe for return flight. When they did their investigation, they found that that object was on the order of 1 millimeter in size. All I'm saying is that if we have a way to increase space situational awareness for objects of that size class, then maybe next time we'll be able to avoid a multi-million-dollar failure and get our astronauts safely home a few months earlier. So that begs the question, how do we begin to detect such small debris? And the state of the art in ground-based surveillance, especially when it comes to optical methods, is often affected by variations in atmosphere, weather, and lighting conditions. Now, I know there are some people from Leo Labs in the audience, so I will admit that there have been some improvements in being able to detect smaller objects from the ground. I know Haystack goes down to about 5 centimeters, and the latest S-band proprietary technology from Leo Labs claims to be able to go down to about 2 centimeters. But there aren't many such stations, and the areas of space that they can swap are relatively small. So it's definitely a step in the right direction, but there is a lot of work to do on all fronts. That's why there has been some research going on leveraging in-space sensors for detecting and improving tracking of these RSOs. In particular, commercial star trackers have been especially attractive because there are thousands of them in space, especially with the recent proliferation of microsatellites with Starlink and the like going up prolifically in the last couple of years. Now, the focus of the past few years of research on this topic has been on improving detection and tracking for RSOs that are already in the catalog, so those that are larger than 10 centimeters. But we asked, if we're already taking space-based measurements, why stop there? Can we use these same star trackers to detect debris that's smaller than 10 centimeters in characteristic length? And that drives our key question for today's conversation, which is, what is the parameter space across debris size, distance, and brightness for which it's feasible for a given star tracker to see a given debris particle? Now that we have our question, we can talk about the model. And in particular, one of our key metrics is apparent visual magnitude, or AVM, which is used to determine RSO visibility. And we combine that with the Barker model for near-Earth objects illuminated by the sun, which relates AVM to optical cross-sectional area and distance from the observer. That's this green equation right here. This equation is particularly useful for satellites where you might already have the geometric and optical information from which to compute A-opt. But for debris particles that aren't currently modeled, that aren't currently being tracked, then we need another model to supplement that to give us A-opt. So we refer to the Interagency Space Debris Coordination Committee standards of modeling them as Lambertian spheres with a phase angle of 0 degrees and a reflectivity of 10%. Combining these two together, we get a relatively simple relationship among AVM, RSO to CST distance, and debris diameter, which is this blue equation at the bottom here. What does this mean? Given, with this simple model, a given particle of debris and its size, its distance from the sensor, we can determine how bright it appears to be to the CST. And from there, compare it to the sensitivity limit of that star tracker to find out if the star tracker can see it. With that defined, and with the clicker actually working, we're going to spend the rest of this presentation focusing on the two key figures from the paper, breaking them down and building them back up to answer that question. And so on this plot, on the y-axis, we have apparent visual magnitude, and on the x, we have distance in kilometers in log scale. And we start by plotting the sensitivity cutoff values for 3 representative star tracker classes using data we've adapted from a paper from Zaharov et al. And in particular, in order from worst to best, at the bottom, we have the nanosatellite sort of budget star trackers. In the middle, we have the more prolific microsatellite class star trackers. And on top, we have higher performing star trackers, which are essentially specialized imagers that you can use for the same purpose. I will note at this point that apparent visual magnitude is reverse logarithmic. So the higher something is on the scale, the more difficult it is to see and to detect, which is why the HP CSTs are on the top. They can see the most in space. Because microsatellite class star trackers are the most prolific, we've also added a green feasibility region underneath that middle blue line. And from there, we can begin the discussion and establish, we've begun the discussion. We can begin the baseline discussion, which is that this red dotted line depicts ABM versus distance for a baseline 10 centimeter pop ACS nanosatellite using the data adapted from Gazdia's ground-based measurements from a few years back. This curve is of particular interest because, again, it's from ground-based measurements, so we know they're real. But beyond that, because it's a 10 centimeter nanosatellite, it serves as a very useful baseline against which to compare the results that we have from our simplified model for 10 centimeter debris particles. Speaking of, that's this thick black line. We see that because it is slightly above the red line, that means that it is dimmer than the nanosatellite, which makes sense to us. It's debris, it's not a metallic object, but not by a whole lot. So they are relatively close. In comparison, when we look at this gray line for 1 centimeter debris particles, we find that the difference is quite a bit more substantial. We've gone from 10 centimeters to 1 centimeter. That's a factor of diameter reduction of 10 and a factor of optical cross-sectional area reduction of 100. So it makes sense to us that it's a lot more difficult to see and for our star trackers to detect. Now, I think that does it for all of the curves that we have on here. So now we can begin to focus on some particular points of interest. Looking at the intersection between our blue micro line and our various debris lines, we find that our model indicates that microsatellite class star trackers can see 10 centimeter debris out to 50 kilometers and 1 centimeter debris out to 5 kilometers. Looking at the nanosatellite star trackers, we have 10 centimeter debris out to 25 kilometers and 1 centimeter debris out to 2.5 kilometers. And for the specialized imagers, our model suggests 10 centimeter debris out to 400 kilometers and 1 centimeter debris out to 40 kilometers. We're about to move on to the next plot, but before we do, I want to indicate that this has been a figure of AVM versus distance parameterized across debris size. And the one that will follow will show essentially the same information, but AVM versus debris diameter parameterized across RSO to CST distance. Once again, we start with our horizontal lines for the various AVM cutoff values adapted from Zaharov. We highlight our green region for the proliferated microsatellite class star trackers. And we start drawing our lines. This first light green line corresponds to an AVM versus size at 1 kilometer sensor to object distance. A slightly darker green line at 10 kilometer range, and an even darker line at 100 kilometers range. There is a general trend here, which is that as distance increases, the objects appear to be dimmer, so detection becomes more challenging, which is not surprising. But in particular, we find that at distances as close as 1 kilometer, even the most budget star trackers that we looked at should be able to detect 1 centimeter and larger debris. Once we get to 10 kilometers, we start to see some limitations, and microsatellite class star trackers can only detect 2 centimeter and larger debris. And at 100 kilometers, we're looking at the higher performance star trackers to detect 10 centimeter and smaller debris. With all of that laid out, we can start to talk about some key takeaways. In particular, using the Lambertian sphere and Barker models, we find that our hypothesis might in fact have been correct. Orbital debris less than 10 centimeters can be detected by commercial star trackers. And in particular, the microsatellite class star trackers can detect 10 centimeter debris at 50 kilometers and 1 centimeter debris at 10 kilometers. The specialized imagers also have the potential to detect debris smaller than 1 centimeter at distances of 40 kilometers and closer. But I will note here that for this particular point, we're going to want to investigate further to see if there aren't any other limiting factors at play that would prevent us from being successful here at such small size scales and such large distances. On the topic of further work, for any sort of further modeling and simulation work, we recommend relaxing the Lambertian sphere and zero phase angle assumptions, just to get something that's a little higher fidelity. For a feasibility assessment, it's not unreasonable to use these assumptions, but for anything higher fidelity than that, we want something a bit more practical. And now that we've shown that detection is feasible, the next step is to investigate tracking of small scale RSOs to help us reach our ultimate goal of using this method to increase and improve our catalog to include those smaller objects as well. That does it for my slides. I think we have 3, maybe 4 minutes left for questions, so I'll open the floor. Thank you.
So I would suggest you go out to the conference that Lincoln Labs is on in May. You might find some discussion of this kind of work.
Okay.
There are some issues with this. One is that a lot of commercial star trackers, the output is quaternions. Their job is to track bright stars.
Yeah.
And this is noise to them, so they filter it out.
Yeah.
It's not clear that a lot of commercial star trackers can allow an output that you use. And then you've got the last thing is the tracking bit. It's one thing to detect something.
Right.
So what? Yeah, okay, detectors. Yeah, there's stuff there. Yeah.
There's absolutely.
It's not useful, right? You need to have a way of getting it tracking and propagating it and picking it up with something else. And star trackers, that's not their job.
Right. There's absolutely a lot of legwork that needs to be done to make this practical and applicable to the general SSA problem. I will say that star trackers that already have the algorithms in place to output quaternions will ignore this information, but there are star trackers out there that will take the images, and from there you can use machine learning or other methodologies to extract the necessary information. In particular, I understand from my conversation with Mr. Wood over there that Northstar is already working on optical systems that can use essentially the same methodology to track such objects using space-based methods.
Yeah, and the Darkness Spacewalk program and pinging anyone who's interested to look into star trackers for SSA. It's big right now.
It's big right now. And this is just the first step to being able to show that we can do the same thing for objects that are smaller than 10 centimeters.
Maybe you just partially answered this question with the Northstar reference, but do you have any plans to fly a payload or partner with any companies to test this on orbit? It's maybe a long way away, but I'm just curious if you see that in the future.
If I can get funding for it, absolutely.
You got it.
And into your future work, you have to take into account the speed of the object
Yes.
that you're trying to detect.
Yes.
If something's moving that fast, the integration time is just not there.
Yes.
Detect it's going.
And
You're already removing the zero Lambertian sphere, but the
Yeah.
integration time on that star tracker, these are small objects, small apertures, big things, integration time is fast. Yeah, you're just moving too fast.
absolutely.
To get that.
And
You
as
have to put that into it.
As I mentioned, our next paper, the abstract, which is under review, is going to be looking at the limitations to our findings here, and that being this.
I just wanted to ask about, if it's one thing to detect and then determine, its orbit as an example, we're talking again about the identity of things in space to identify it as this object. So I'm wondering if that were to happen, that you would try to put something into a point cloud and say, no, we may not know the identity of that 1 centimeter size particle, but we have these number of particles, and we can put that into a point cloud and maybe use the point cloud as a way of determining the orbit of the cloud itself.
Exactly.
That's a possibility.
I think that's a good thought. Yeah, it's certainly one potential application of this methodology to integrate it with existing orbital debris models and using that to say propagate clouds as compared to individual particles. Yes.
Given the short distances that you need to be from the object to detect the small objects, what kind of scale are you talking about? How many objects are you being able to track and observe at one time?
That is the fundamental question that I would like to answer with my dissertation. But essentially, when I say that we have thousands of eyes in space, the hope is that the more eyes we have, the more star trackers we have, the more objects that we'll be able to catalog in this way. If no one asked, since no one has asked this question yet, I will ask, does anyone wonder, with the scales that we're talking about here, how does that compare to stars that we see? Like 1 centimeter out to 40 kilometers is about 4e6 of a difference. I won't take too much time because I'm being told to stop, but if we look at the corresponding ratios for real stars, for example, Betelgeuse, you find that they're roughly comparable or bigger. So these ratios are in fact quite reasonable. Thank you.